In this video, we're going to take a look at the washer method. The washer method is a variation of the disk method that we learned in the last video, except now that we have two functions. So if we look over here, we have two functions, f of x and g of x. And we want to take the region in between these two functions and rotate it around the x-axis. And so when we do that, we're going to have a cavity in the middle of it because there's going to be a hole, and that hole will be because of this space right in here. And so you can kind of see that if you take a look here. You've got the function, the outer function, which is this function right here, and it's being rotated around. And then you've got the inside function, which is g of x, and it's being rotated around. And so what you have, as messy as this looks now, you've got something that looks like a washer, right? You've got the outer circle, and then you've got the inner circle. So this would be created by the outer circle f of x, and then the inner one from g of x, rotated around, and so you've got all of this volume that looks kind of like a washer. And of course it has thickness too, all right? So this is why it's called the washer method. Now, what we're doing is the same idea as with the disk method, that we're taking a bunch of rectangles and rotating them around, and we're going to create a volume that looks something like this. Now, to develop the formula, let's go back to we know that the formula for the disk method was pi, the integral of pi times f of x squared dx from a to b. But now we have two functions. And so if we want to find the radius squared, that would be the area of the circle. If we just take the larger circle, that would be f of x squared times pi. That gives me the area of the outer circle. And then if we take the area of the inner circle is going to be pi times g of x squared. And again, it might be easier to see if I just draw this from a sideways point of view. So we've got outer circle and an inner circle. And so this is the outer circle. That gives me the area of the inner circle. All right. But what we want is the difference between those two. So what we're going to do is we're actually going to subtract them. So we take pi times f of x squared minus pi times g of x squared. Well, if we factor out the pi, then what we end up with is pi times f of x squared minus g of x squared. And that gives us the formula that we're looking for the washer method, all right, which is right down here, okay? So volume is equal to the integral from a to b of pi times f of x squared minus g of x squared. Important thing to remember and to know is that f of x squared is your outer circle. That's going to be the bigger circle. And then g of x squared is going to be the inner circle. And so we subtract them and we get this area in there. And that's what we're looking for. And then we take that area and we multiply it by dx, which gives us the width of this little, or the thickness of that washer. And then we have the volume. So that's the formula, and that is the development of the formula very quickly. I'm not going through the whole details with the rectangles and everything. It's the same idea. We develop a whole bunch of rectangles. We rotate those rectangles around the axis, and we create disks and washers, and then we add them all together using Riemann sums. So let's just do a couple of problems here real quick. Number 1, exercise number 5. Find the volume of a solid of revolution formed by revolving the region bounded above by the graph f of x equals x. That would be this. And below by g of x equals 1 over x, which would be this. And so we're looking for the area in between there to be rotated about the x-axis. So we're rotating it about the x-axis. And so kind of use your imagination again here. And so you can see that you're going to have a hole in the middle. The hole in the middle is going to be from this space in here that is empty, and then that's being rotated around the x-axis. So here's the procedure. First of all, we need to know the point of intersection. We need to know where these two graphs are intersecting because it doesn't give us bounds of integration. It just says the region bounded above and below. So you can use Desmos to do this, or you could just do it algebraically, set the two equations equal to each other, and then solve that. You get x equals plus or minus 1. We're in the positive quadrant, so we just want x equals 1. And so the other boundary is x equals 4. We were given that. So our bounds go from 1 to 4. And then we need to determine, I didn't write it on this one, but the outer ring. What is the outer ring? Okay, the outer ring is function f of x. That's the one that's farthest away from the axis of rotation. The inner ring then, the inner ring is going to be the function that's closest to the axis of rotation, which is the x-axis. That's g of x, which is 1 over x. So that helps us to put our integral together in that formula. And so we have that over here. The volume is equal to pi, integrated from 1 to 4, our outer ring, f of x squared, minus our inner ring, 1 over x squared, times that whole quantity times dx. Once you've got the integral set up, it is now just a matter of integrating. And so integrating, we end up with this. Evaluating that at 4 and 1, we end up with this. And then we end up with the volume being equal to 81 pi over 4. And again, you can check this in Desmos. Put your original integral into Desmos. It will give you a decimal number. Convert 81 pi over 4 to a decimal number. See if they agree. So some of the important points here is find the points of intersection if you're not given them. If you have to find them, use Desmos, use algebra. Identify your bounds. So what are the bounds on the x-axis, the bounds of integration? Then what's your inner ring and what's your outer ring? The inner ring is always closest to the axis of rotation. The outer ring is the one farthest from the axis of rotation. Exercise 6. Find the volume of the solid obtained by rotating the region bounded by y equals 9x to the fourth and y equals 9x about the x-axis when x is greater than or equal to 0. So again, you can graph this in Desmos, and you're going to get this region in here. And this is the region that we are rotating around the x-axis. So here's our axis of rotation, the x-axis. Okay. To find the point of intersection, again, use Desmos, or you can use some algebra. When you use algebra, it's going to involve a little bit of factoring, and you're going to end up with x equals 1. Probably be easiest just to use Desmos. So the other bound of integration is 0. So we have 0, and we have that at 1. 1 and 0. So we've got that. What is the outer ring? Well, the outer ring is the function that is furthest from the axis of rotation, which again is down here. So clearly 9x is farther away from the axis of rotation. So that becomes our outer ring. 9x to the fourth is closer to the axis of rotation, so that becomes the inner ring. And so we want to square each of those. So we have 9x squared minus 9 to the fourth, 9x to the fourth squared. We're subtracting them. We're multiplying it by pi and then integrating the whole thing. Setting up the integral is half the battle, as I've said many times before. Once you've got that, square 9x and square 9x to the fourth, you get this. And then finally, integrating that, 81x squared is 81x cubed over 3, and 81x to the ninth over 9. Yes, those could be simplified, and ultimately it becomes 18 pi. Check that with Desmos. Okay. Now, so far, we have rotated around the x-axis. Well, we can also rotate around another line that is not the x-axis. In this particular problem, we are rotating about y equals 6. So the procedure is exactly the same, but there's just one little added thing that you need to be thinking about. So go to Desmos if you need to draw the graph. Here is the graph of 3 to the negative x. Here is the graph of y equals 3. X equals 4 is right here. And so we want the region bounded by those. That would be all of this. Now, we're not rotating it around the x-axis. We are rotating it around the line y equals 6. That is our axis of rotation. So, first thing we do is find the bounds. Well, the bounds are from 0 to 4. This is 0 and 4. That's pretty straightforward. The outer ring. Now, remember, the outer ring represents the radius. And so I have always said the function that is farthest away from the axis of rotation is the outer ring. Well, 3e to the negative x is the furthest away, that's this, from the axis of rotation, which is up here, okay? But what we want is we want this distance from here to here. We're creating a rectangle that's from 3e to the negative x to the axis of rotation. So I'm just going to draw a little rectangle in there. And so we're rotating that around here. The radius of that is going to be this distance. This distance is going to be 6 minus the function. Okay? So 6 is the distance, 6 is the distance from the x-axis to the line. That's this distance. And then this function is, the other distance in here, so we want to basically subtract them. Okay, this distance is 6 minus 3e to the negative x. So I hope I made that clear. Now, we need to find this distance right here from the inner ring. The inner ring is going to be the distance. Let's kind of get rid of some of this stuff. The inner ring is going to be the distance from my inner function. So that's just this distance here. My inner function is the function 3. Just y equals 3 to y equals... So what's the difference between y equals 3 and y equals 6? Take the difference between them again. Same thing. 6 minus 3e to the x. 6 minus 3, which is just 3. Think about that a little bit. Kind of visualize it in your mind. When we're finding the outer ring, in the inner ring, what we're really doing is we're finding the radius. Okay, so this is going to be equal to the radius, and this is the outer radius, the inner radius. The inner ring radius, the outer ring radius. All right, so then once you've got all that, you just put it together in your formula. Pi comes out, integrating from 4 to 0. Here's my outer ring, 6 minus 3e to the negative x squared, minus my inner ring. Simplifying all that, you get this. Oh, we got a lot more here. And then simplifying some more, you get this. Be real careful with the algebra. And then integrating, we get this. I mean, you know, you can go through and do the algebra and do the integrating. My major concern here is showing you how to set these things up. I am going to assume in many of the problems that I do that you can do the algebra, that you can do the basic integration. And then from here, it's just arithmetic. You've integrated, now you're plugging in 4, you're plugging in 0. Again, if you want, just let Desmos do that. This is another nice thing to do with Desmos. Once you get your antiderivative right there, once you get this, you can just type that into Desmos as a function and then evaluate it at 4 and evaluate it at 0 and subtract them if you don't want to do all of that by hand. Now, in WebAssign, they do want algebraic answers. So that's about as simplified as you're going to get algebraically. Yes, some of the answers in WebAssign are pretty icky looking. But again, you can take this and you can convert it into decimal, put your original integration problem and into Desmos and see if they agree. So this is an example, once again, of rotating around a line other than the x-axis. All right, now here it talks about washer method for solids of revolution around the y-axis, but that's not what the following problem is about, okay? The following problem is similar to the last one, but we can revolve around the y-axis. It's similar to what we've been doing, except we're doing it about the y-axis. Similar to when we did an example with the disk method around the y-axis, we can do the washer method around this y-axis, same idea. So here's another one where we have an axis of rotation other than one of the axes. So find the volume of a solid of revolution formed by revolving the region bounded by f of x equals 4 minus x, that would be this line, and below by the x-axis. All right, so we're taking this region here, it's a triangular region, and we are rotating that about the line y equals -2. All right, so when we rotate that about this line, we're going to have a big hole in the middle of it. And so we go through the steps. What are the bounds of integration? Well, the bounds of integration are from 0 to 4. Got that. Now, what is the radius of the outer ring? The radius of the outer ring is the distance of a rectangle from here to here. What would be the height of that rectangle? Well, the height of that rectangle is going to be the distance from the x-axis to here, which is the function value. Put that in another color. That's going to be from here to here. That's the function value. And then this distance, which is a distance of 2. And so to be consistent with the way we did it, subtracting, you're going to take the function value, 4 minus x, that gives us this, minus the -2. Well, notice that minus the -2 becomes plus 2. So 4 minus x plus 2 becomes 6 minus x. So the distance here is 6 minus x. Likewise, the inner ring is from the x-axis to here. Well, that's just the distance of 0 minus a -2. 0 minus a -2 is, of course, just 2. And once you've got that, I think in these washer problems, when you're revolving around some axis other than the x-axis, the hardest part is making sure that you get the inner radius and the outer ring radius correct. If you've got that, this is the outer ring, and this is the radius of the inner ring. So you just put it together in your integral now. The outer radius squared minus the inner radius squared. Simplify it a little bit. Simplify it a little bit more. Take the antiderivative. Evaluate the antiderivative at 4 and 0, and we end up with 160 pi over 3. All right, so quite a few problems here. Hopefully you are finding these videos helpful. So let me know if you have any questions. See you in the next video.